All right, so have you ever just like really stopped and thought about the sun's path across the sky, each day?
It does seem pretty straightforward, right? Just that arc.
Yeah, yeah, but like what if it wasn't so direct? What if it was, I don't know, tilted, a slanted
A
track?
slanted track that not only dictates the seasons, but also holds secrets to predicting like huge events, cosmic events, like eclipses.
Eclipses, exactly. It's almost like crazy to think about how ancient thinkers, they didn't have our fancy tools, but they could map these super subtle movements so accurately.
It is amazing. It speaks to, I think, this human drive to find order in the universe, wouldn't you say?
Totally, totally. That like the simple things we see in the sky had these underlying structures we can actually predict. It's it's this thread that runs through like all of human history across cultures and time.
Across millennia, absolutely.
And that curiosity is really what we're diving into today, exploring this ancient wisdom to kind of deepen our own understanding of the cosmos.
Yeah, and today we're focusing on the insights of Aryabhata.
Aryabhata, yeah, 5th century astronomer from India,
Mhm.
and his ideas were like way ahead of his time.
Centuries ahead, some of them, yeah. Aryabhata is a really important figure in the history of astronomy. I mean, he lived in a time with a lot of diverse cosmological beliefs. But his work it presented this, I think, sophisticated and really coherent understanding of how things move up there.
And so in this deep dive, what we're going to do is unpack two verses, really key verses from his work, the Aryabhata,
Okay.
verses 8 and 9.
Right.
And in these verses, Aryabhata details the sun's, what we call the ecliptic, the slanted path, and the precise angles that go with it.
It's really cool. These two verses are, I think, particularly interesting because they combine this observation with mathematical reasoning.
Yeah.
Verse 8 kind of paints a picture, right, of the sun's journey each year, and then verse 9 comes in and gives us this quantitative framework, the measurements that really underpin that journey.
Okay, so to really get this, let's go back in time for a second.
Yeah.
Imagine it's the late 5th century. Okay, we're in Kusamapura. It's this like intellectual center in the Gupta Empire. You can picture scholars, maybe they're gathered by torchlight, right? They're looking at scrolls,
Debating.
debating about the nature of the cosmos.
Yeah, and think about it. They didn't have telescopes. Direct observation was everything. They had to rely on, meticulous tracking of these celestial bodies, and then some pretty ingenious math to really figure out how the universe worked.
And in this environment, Aryabhata, he makes a truly groundbreaking contribution.
Yeah.
He realizes that the Earth rotates on its own axis every day.
Yeah.
Now, his model, it still puts the Earth at the center, right? That was the common view then. But understanding that spin, that was huge.
It was a revolutionary idea. I mean, the geocentric model, that lasted for centuries after Aryabhata, but him saying the Earth spins, that was a big step towards our modern understanding of the solar system. It shows like how good his observational skills were and how willing he was to put forward ideas that weren't, the norm.
So building on what we've already talked about, the scale of Aryabhata's cosmos, right? We're going to focus in on the movements of the celestial bodies, specifically the sun's path, that yearly path against the backdrop of what they thought of as this celestial sphere.
Right.
And this slanted path, we're calling it the ecliptic, is key. It explains so much. The seasons changing, eclipses, even agricultural cycles. Like,
Yeah.
it was fundamental back then.
It really was. It was a practical matter as much as it was an intellectual one.
Okay.
The concept of the ecliptic, it's a cornerstone in understanding how things move in the heavens. It's a stable reference point, and from that we can understand how, the moon moves, how the planets move, all of that.
All right, so let's dive in. The term we use now for this slanted path
Yeah.
is, as you said, the ecliptic.
Right.
It's the sun's apparent journey over the year as we see it from Earth. And our exploration, this starts with verse 8 of the Aryabhata, where Aryabhata maps this whole thing out for us.
And this verse it's really elegant, it's concise, it describes this annual movement in relation to the celestial equator, and it really just divides the sun's path into two halves.
Okay.
And that's how we get our seasonal transitions.
So verse 8 is in Sanskrit. It reads, Mede kanyante samam udagapaman talat kagalardam, talibimanante shirhat dakanaivafa. Now, I'm no Sanskrit scholar, but a rough pronunciation is Meshade kanyantum samum udugupamondular kagulardam, toli adirminantum shai shadam dakshinainu. And this is basically laying out the sun's entire yearly journey in relation to, as you said, the celestial equator.
It is, and it's structured so beautifully, the symmetry, half the year the sun is north of the celestial equator, half the year it's south. So to picture this, right, think of the celestial equator like this imaginary circle in the sky directly above Earth's equator. It's like our baseline for understanding how things move up there.
And in this verse, we see the term apamatala, which, as we mentioned, is the ecliptic, the sun's apparent path. And remember, Aryabhata's view is geocentric. Even though he knew the Earth spins, in his model, the sun's going around a stationary Earth along this tilted path, this ecliptic.
Right, and that tilt, that angle of the ecliptic, that's the key, because that's what causes, different parts of Earth to get different amounts of sunlight throughout the year, and that's what gives us the seasons.
Okay, let's break it down. First part. Meade kanyantis samam udigapan talat kagolardam.
Right.
And that translates to something like from Aries to Virgo, equally to the north of the ecliptic, half of the celestial sphere. So that's basically like March to September in our modern calendar.
Yeah.
What's he saying about the sun's position during those months?
He's saying that for those 6 months, from our perspective here on Earth, the sun appears north of the celestial equator. So for listeners in the northern hemisphere, that's when you have spring turning into summer, culminating around the summer solstice. That's when the sun reaches its highest point in the sky, appears to be in the constellation Cancer. Longest days of the year for the northern hemisphere because that part of the Earth is tilted most directly at the sun.
Makes sense, thinking about our seasons, yeah. And then the second part. Tel yeraminanti sherhagdo dakinaiva. So from Libra to Pisces, the remaining half to the south. That's like September to March.
Exactly. And now the sun appears south of the celestial equator. So for the northern hemisphere, that's fall into winter. Shortest days around the winter solstice, sun's lowest in the sky appears in Capricorn. Northern hemisphere tilted furthest away from the sun.
And the words kagalardam and Chirtha, those just highlight that the ecliptic splits the celestial sphere in half, right, over the whole year.
That's right. It emphasizes this cyclical, predictable nature of how the sun moves in relation to that celestial equator.
And the ecliptic doesn't actually perfectly line up with the celestial equator. It crosses it at 2 points, right?
Right.
Aryabhata mentions them. Aries, which marks the vernal equinox or spring equinox, and Libra, which marks the autumnal or fall equinox.
Yes.
And the equinoxes, those are the times when day and night are roughly equal all over the globe, right?
Yeah, those are the transitions, right? Sun moving from the northern celestial hemisphere to the southern and vice versa. That drives the changes in the seasons.
So I think it's important to really visualize this tilt. It's hard to picture, right? So think of it like two hoops. One hoop is the celestial equator, lying flat. The other hoop is the ecliptic, and it's tilted relative to that first hoop. That angle, that inclination, that's why we have seasons. If there was no tilt, we wouldn't have this variation in sunlight throughout the year.
Yeah, it's a great analogy. The angle between those two hoops, that determines how intense the seasons are, how different summer and winter are. And Aryabhata gets into that angle, that specific tilt, in the next verse.
Okay, so verse 8 gives us the map, the framework for the sun's journey, and verse 9 comes in and gives us the measurements, the specific tilt, and also information about how other celestial bodies, wobble relative to the ecliptic.
Yeah, we go from the qualitative to the quantitative. Verse 9 gives us the numbers, the angles, the hard data behind what we see happening up there.
All right, so verse 9 reads, Vapakrama 24, Shashivik Shoryupashifampa Stavidarhota Bugubutayo, rough pronunciation. Vapukramu 24, Shashivikshepam Shadupanchumu for half, Shani Guru Kujuvikshepas, Tadv Vidhardo of Borugubu Dudoyo. Now, this may sound like just a bunch of astronomical terms and numbers, but it's actually packed with data.
It is. Verse 8 gave us the picture, and verse 9 gives us the dimensions of that picture. So let's start with the first part. Hapakrama 24. That's referring to the sun's maximum declination, what we call the obliquity of the ecliptic. And Aryabhata says it's 24 degrees.
Oh.
So can you explain to our listeners what that means for us here on Earth?
So that 24 degrees, that's the angle of the tilt we've been talking about. The tilt of the ecliptic compared to Earth's equator. What it means is, at the solstices, summer and winter, the sun reaches a maximum of 24 degrees north or south of the celestial equator. That's what causes those longest and shortest days.
Exactly. This angle, it determines how strong the seasons are. Bigger tilt, more extreme summers and winters. Smaller tilt, milder seasons.
It's really cool to compare this to modern measurements. Today we know Earth's tilt is about 23.4 degrees.
Right.
But research shows that back then, in 499 CE, it was closer to 23.6. So Aryabhata's 24 degrees, pretty accurate for his time, especially considering, he didn't have our fancy instruments. Maybe he even simplified it a little to make calculations easier.
That slight difference, it really shows how precise these ancient observations were. Aryabhata's measurement, it's within the margin of error you'd expect back then. He really understood how the sun moved across the sky.
Okay, next part. Shashivika Paijadapanya Kama, 4.5. That translates to the moon's maximum latitude, how far north or south it goes from the ecliptic. Aryabhata says it's 4.5 degrees.
Right, so the moon doesn't orbit perfectly in the same plane as the Earth orbits the sun, the ecliptic. It's tilted about 5.1 degrees relative to the ecliptic, on average. Aryabhata's 4.5 degrees, it's a little different from the modern value, but it still shows he understood this important fact, that the moon's orbit is inclined.
And this wobble, this lunar latitude, that's crucial for eclipses, right?
Absolutely. For a solar eclipse, the moon has to be between the sun and Earth. For a lunar eclipse, the Earth has to be between the sun and moon. This can only happen when the moon is very close to 0 degrees latitude, basically right on the ecliptic plane. And it also has to be near one of its orbital nodes. Yeah, those are the points where the moon's orbit crosses the ecliptic plane. We saw this mentioned in verse 4, but we didn't talk about it much. So for an eclipse, the sun, Earth, and moon have to all be lined up in 3D space. Moon has to be near the ecliptic, near a node, and the moon's phase has to be right too. New moon for solar eclipse, full moon for lunar.
So Aryabhata's measurement of this lunar latitude, that's a key piece for understanding when eclipses can happen. It's not just the sun's path, it's how the moon's path intersects with it.
Exactly, 3D geometry. Even within his geocentric model, he's thinking in 3 dimensions.
Next. Shanigurkajabikoposta Tadvihardo. This is the maximum latitudes of Saturn, Jupiter, and Mars are Tadvihardo, which means half of the moon's maximum latitude. So half of 4.5 degrees, that's 2.25 degrees.
Right, and that's actually pretty close to the real orbital tilts of these planets. Saturn's is about 2.5 degrees, Jupiter's is about 1.3, Mars is about 1.85. So Aryabhata's value, it's a decent average, a good approximation for those outer planets.
And finally, Atha Bhugavaya. This means Venus and Mercury have similar maximum latitudes, 2.25 degrees. Now, some people think Aryabhata meant 2 degrees for these inner planets, but 2.25 fits better with the rest of his system in this verse. And again, these wobbles, these latitudes, they explain how these planets move against the background of the zodiac constellations.
Yeah, these values for the planetary latitudes, they might not be as precise as his measurements for the Earth's tilt or the moon's tilt, but they still show that he understood that the planets, just like the moon, don't move perfectly along the ecliptic. They have their own tilts, their own inclinations, and that affects where we see them in the sky.
Okay, so let's recap for everyone.
Right.
Verse 8, we get the picture of the ecliptic, sun's path. North of the celestial equator for one half of the year, roughly March to September, south of it for the other half, September to March, crosses at the equinoxes. Verse 9, we get the numbers. 24-degree tilt, 4.5-degree wobble for the moon, 2.25 for the other planets. All this detailed by Aryabhata way back in the 5th century.
It's remarkable. He created this interconnected system. Ecliptic is the foundation, the tilt gives us the seasons, and the latitudes are key for understanding eclipses and how the planets move.
And remember, this wasn't just abstract astronomy back then. Knowing the seasons, that was crucial for farming. When to plant, when to harvest. The sun's declination, that affected how long the day was, how sundials worked. Predicting eclipses, that was a huge deal, probably had all sorts of religious and cultural significance. And tracking the planets, that likely had astrological meaning too.
It was woven into their lives. They weren't just trying to understand the universe, they were trying to live in sync with it. Aryabhata's system, it gave them a sense of predictability, which would have been so valuable.
And think about it, they did all this without any of the tech we have today. It's mind-blowing. If we run like an AI check on Aryabhata's values, we can see how accurate he was. His 24 degrees for the tilt, it's 98% of the estimated value for 499 CE. And it's 4.5 degrees for the moon. It's 88% of the modern average.
Those figures, they really speak for themselves. Aryabhata wasn't guessing. He was observing. He was calculating. He was a brilliant astronomer.
And that idea of a spinning Earth, even within his geocentric model, that was bold. He was willing to question what everyone thought and come up with new ideas based on what he saw in the sky.
Yeah, he wasn't afraid to challenge the status quo. And even though his model wasn't the same as our modern heliocentric model, His ideas about motion, about the geometry of the solar system, they were really important. He paved the way for later discoveries.
And back then, people saw celestial events as, like, deeply symbolic. Aryabhata's work, it sort of took this perceived cosmic order and made it quantifiable, made it predictable. It wasn't just mystical anymore, it was mathematical.
It was a shift towards scientific thinking. Natural phenomena, even in the sky, can be understood, can be predicted using math.
So as we wrap up our deep dive into these two verses, verses 8 and 9 of the Aryabhata, I hope everyone can appreciate just how much information is in these verses. We talked about the ecliptic, that 24-degree tilt, the moon's 4.5-degree wobble, the planets at 2.25 degrees, all this from Aryabhata centuries ago.
And through these measurements, he gave us a way to understand the seasons, the eclipses, these fundamental things we experience.
And this is just the beginning.
Oh, yeah.
In our next deep dive, we're going to go even deeper into Aryabhata's work, look at his contributions to trigonometry, and see how he used these angles to make even more complex predictions.
Yeah.
So if you're fascinated by this ancient wisdom, like I am, make sure to subscribe to The Deep Dive. Join us as we keep exploring the secrets of the universe, one verse at a time.
Next time, you'll see how he took this understanding of celestial geometry and used it to develop powerful mathematical tools to predict where the planets would be, when eclipses would happen. It's all connected. It's all part of his system.
And for you, our listener, next time you look at the night sky, maybe you'll see it a little differently. How does knowing about these ancient observations, made without any of our technology, change how you view the cosmos, how you view our place in it all? What other seemingly simple things we see in the sky might have deeper meanings, deeper math behind them, just waiting for us to discover? That's something to think about until next time.